Hello everyone, welcome back to our channel gsipucmysuru. This is the fifth session of the third chapter, that is Transistor Amplifier. In the last few sessions we discussed about the different configurations of amplifiers like common base amplifier, common collector amplifier and common emitter amplifier. So in this session we are going to start with the comparison between all three amplifiers configurations. So on the left hand side we are going to see the amplifier parameters. So here we are going to see all the three different configurations, that is the common emitter, common base and the common collector configuration. The very first parameter what we are going to see is the current gain. The current gain in this C mode, that is common emitter configuration type of amplifier, is high, whereas in the common base configuration it is less than 1, and here highest whose value is around 1 plus beta. Here it is just beta, and for the common collector configuration it is 1 plus beta. So the next parameter is the voltage gain. The voltage gain in the common emitter amplifier circuit is high. Here it is moderate, and in the common collector it is low. Coming to the third parameter, that is the power gain. The power gain in the common emitter configuration is the highest, and for the common base configuration it is moderate, and for the common collector configuration again it is moderate. So this is the power gain comparison. After that we are going to see the phase shift. In the C mode there is 180 degree out of phase shift, that is the output signal is 180 degree out of phase with the input signal, whereas in the common base it is in phase, and in common collector also it is in phase. Input impedance. Input impedance in common emitter is moderate. In the common base it is low, whereas in the common collector it is high. Next comes the output impedance. Output impedance in the common emitter configuration is moderate, whereas in the common base it is high, and in the common collector configuration it is equal to low. Coming to the last parameter, that is the bandwidth. Here in the common emitter configuration the bandwidth is narrow, whereas in these two configurations the bandwidth is wide. So this is the comparison table of three amplifier configuration, that is common emitter, common base as well as the common collector configurations. Next we are going to see with the AC and DC analysis, or the AC and DC equivalent circuit of an amplifier. In an amplifier both the type of sources are connected, that is AC source kuda connect ಮಾಡ್ತೀವಿ ಹಾಗೆ DC source kuda connect ಮಾಡ್ತೀವಿ. The DC source is connected in order to give the biasing condition for the amplifier, whereas AC source is connected in order to give the input signal to the amplifier. That is the input signal whatever is needed to be amplified, that will be applied across the input of the amplifier amplifier which is nothing but an AC signal. So AC ಮತ್ತು DC ಎರಡು signals ನ ನಾವು ಈ transistor amplifier ಗೆ apply ಮಾಡ್ತಾ ಇದ್ದೀವಿ. So now we are going to see how to analyze this DC currents and DC voltages and the AC currents and AC voltages, because all of these are present in one particular circuits. So now let us try to understand that with the help of a circuit. This is the circuit what we are having in order to find the analysis of AC and DC. So what is this? This is nothing but a common emitter configuration type of amplifier. This is the emitter terminal, base and a collector, and this is an NPN type of transistor. So we are going to apply the input signal, that is nothing but Vin, between the base and the emitter terminal, and the output is extracted between the collector and the emitter terminal. Here, in order to do the analysis, we have to do the DC and the AC analysis separately. That is, we need to measure the AC voltage and current separately and the DC voltage and current separately. So first let us do the DC analysis. In order to do this DC analysis, what we have to do is, we have to remove this AC source and open this capacitors. So ಇಲ್ಲಿ ಎಲ್ಲೆಲ್ಲಿ capacitors ನ use ಮಾಡ್ಕೊಂಡಿದ್ದೀವೋ those capacitors has to be removed and this AC source should be open circuited, that is it has to be completely removed. Why we are going to open these capacitors? Because these capacitors will block the DC signals, that is DC current ಆಗಲಿ ಅಥವಾ DC voltage ಆಗಲಿ block ಮಾಡುತ್ತೆ ಇದು. ಹಾಗಾಗಿ ಈ capacitors ನ ನಾವು remove ಮಾಡ್ತೀವಿ. After removing this capacitors and the AC source, we'll be left with only a only a transistor with 4 resistors, R1, R2, and this is grounded. Here we'll be having RC, here RE, RC, R1, R2. This is an NPN transistor, and here plus VCC. ಹೌದಲ್ವಾ? Because these capacitors will be removed. ಇದು ಎಲ್ಲ capacitors open ಮಾಡಿಬಿಡ್ತೀವಿ. ಹಾಗೇನೆ ಈ Vin, that is the input voltage source, will be completely removed. So let us consider this as the voltage V2, that is the voltage across R2 is written as V2, and this voltage will be written as, this is the emitter terminal, base and the collector terminal. So here VBE, that is the base to emitter voltage, idu base to emitter voltage, and the voltage across the collector and the emitter terminal will be denoted by VCE. The current which is flowing through this RE, let us denote it by IE. So here V2 is nothing but the voltage across this resistor R2, and this V2 is forward biasing this base to emitter junction. So V2 can be written as, V2 is equal to VCC into R2 divided by R1 plus R2. V2 can be calculated by applying the voltage divider rule. So V2 is equal to, the source whatever I am applying is VCC, VCC into the resistor across which I am measuring the voltage, that is R2, divided by sum of these resistor R1 and R2. And V2 is forward biasing this base to emitter junction ಆಗಿರೋದ್ರಿಂದ V2 is equal to the voltage drop across this junction, that is the base to emitter junction, and the voltage drop across this resistor RE. So V2 is equal to the sum of this and this voltage drop, that is VBE plus the voltage drop across RE, let me denote it by VE. ಆಯ್ತಾ? So VBE plus VE measure ಮಾಡಬೇಕು ಅಂತ ಹೇಳಿದ್ರೆ the current which is flowing through that resistor into that resistance value, that is IE into RE. So this is V2, but IE is equal to V2 minus VBE divided by RE. So this is one formula and this is another formula. I2 is equal to V2 minus VBE by RE. Now let us apply the KVL across the output terminal. So that is equal to VCC is equal to the voltage drop across this resistor plus the voltage drop across this junction plus the voltage drop across this resistor. That is IC into RC, the voltage drop across the resistor RC can be calculated by the product of the current flowing through that resistor and its resistance value. IC into RC plus VCE plus IE into RE. IE into RE is nothing but the voltage drop across this particular resistor. So this is another formula. By using these three equations, that is V2, IE and VCC, by using these three equations, we can easily find out the DC voltage and the DC currents. Clear? Now let us try to do the AC analysis. For the AC analysis, we are going to short the DC sources and also the capacitors will be shorted. Since this capacitor will be shorted, ee capacitor na nanu short madide anta helidre, even this entire thing, that is RE, will also be shorted because adu parallel agide. So RE na nanu illi remove martini. And here, since even this capacitor is shorted, ee capacitor na short madide anta helidre, that collected terminal will be connected to ground through this RC. So ಏನು ಮಾಡಿದ್ದೀವಿ ನಾವು ಇಲ್ಲಿ RC ನ ನಾವು ಈ ತರ ಬರ್ತಿದೆ. So this is the final circuit which we are going to get after shorting the DC as well as the AC sources. This is the first step. In the second step, what we are going to do is we are going to replace the emitter and base junction with a AC resistance. AC resistance ಇಂದ ನಾವು replace ಮಾಡ್ತೀವಿ. Along with that, the collector and the base junction will be replaced with a current source. What we are going to do is, we are going to delete this and we'll be getting a circuit like this. A current source and here a resistor RC, and this will be named as beta times of RE dash, and this is beta times of IB. This is the current which is flowing, IC, emitter terminal, collector terminal and the base terminal. And the resistance, when is looked towards this base, then that will be called as the Zin base. So R1, R2, Zin base, and this is the current source what we are going to use. The emitter and the base terminal will be connected through the resistance. Collector and the base junction will be replaced with a current source, that is beta IB. Now in order to do this analysis, what we have to do is we have to see the parameters separately, that is the input impedance enagirutte, output impedance eno, voltage gain eno, all these things must be seen separately. This transistor is nothing but two diodes which are connected back to back. So whenever a small AC input signal is applied, the emitter diode will not rectify the signal, but instead it provides a small amount of resistance, what is called as AC input resistance, that is denoted by RAC. This RAC is nothing but the resistance offered by the emitter diode, and the collector diode act like a current source as usual. Here the collector diode na jagadalli we have written a current source. So adu collector diode as usual agi namge current source tara behave ಮಾಡುತ್ತೆ. This RAC can also be called as the Zin base. Now let us try to understand all of these parameters, that is input impedance, output impedance separately. The input impedance, when it is looked into the base side, this input impedance will be denoted by Zin, which is nothing but the ratio of input voltage Vin to the input current In. Since we are doing the AC analysis, let us denote it by small letter In. But this input impedance, when it is looking towards this base current, I am having three different resistors, R1, R2 and the Zin base. So Zin is nothing but R1 parallel to R2 parallel to Zin base anta ಹೇಳ್ತೀವಿ. So this Zin base has to be calculated. Zin base, when it is looked directly towards the base terminal, Zin base is equal to Vt, that is nothing but the thermal voltage, divided by input DC base current. Vt is nothing but the thermal voltage divided by input DC base current. So Vt divided by the base current DC anta helidre, that is nothing but Ip. But we know that beta is equal to Ic divided by Ib, and Ib will be equal to Ic divided by beta. The same thing we are going to replace here. Z in base is equal to Vt divided by Ic divided by beta anta barutte. That beta can be written in the numerator. So that is Z in base will be equal to Vt into beta divided by Ic anta ಹೇಳ್ತೇವೆ. But in the transistor, Ic is approximately equal to IE itself. Ic ಮತ್ತೆ IE value ನನಗೆ almost same ಇರುತ್ತೆ. So that Z in base can be written as Vt beta divided by IE. But this Vt divided by IE can be replaced by Re dash. So the remaining is Re dash beta. So Z in base will be equal to Re dash into beta. And in this particular expression, Z in base can be replaced by R1 parallel to R2 parallel to Re dash into beta, which gives me the input impedance Zin. So this is the formula what we are going to use in order to calculate the input impedance. Similarly, we have to find out the output impedance. So Z in base anta helidre Re dash times of beta, and Z in input impedance ನಾನು ನೋಡಬೇಕು ಅಂತ ಹೇಳಿದ್ರೆ ಅಥವಾ ಇನ್ಪುಟ್ ಇಂಪಿಡೆನ್ಸ್ ನ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಬೇಕು ಲುಕಿಂಗ್ ಥ್ರೂ ದಿಸ್ ಬೇಸ್ ಅಂತ ಹೇಳಿದಾಗ R1 parallel to R2 parallel to this Z in base. Let me erase this diagram and write the formulas. So Z in is equal to R1 parallel to R2 parallel to Z in base, whereas Z in base will be equal to Re dash times of beta, where Re dash is equal to Vt divided by IE. Vt is nothing but the thermal voltage whose value is equal to 26 millivolts for silicon and 52 millivolts for germanium. So this is Vt. Now let us calculate the output impedance. The output impedance denoted by Z0 is nothing but the ratio of output voltage divided by output current. The output voltage is nothing but the voltage which is measured across the resistor Rc, that is Ic into Rc divided by Ic. So Ic gets cancelled, so I will be left with only Rc. So Z0 is equal to Rc. If RL is connected across this, RL is nothing but the load resistor what we are going to use. If RL is connected, then Z0 will be equal to Rc parallel to RL, only if RL is calculated. If not, Z0 value is just Rc. Z0 is equal to Rc or Rc parallel to RL if the load resistor is connected. Now let us try to find the expression for the voltage gain, that is equal to AV. The voltage gain which is denoted by AV is nothing but minus of output voltage divided by input voltage. Why the negative symbol is written over here? Because here I am considering a common emitter configuration. In the common emitter configuration, the output voltage is 180 degree out of phase with the input voltage. ಹಾಗಾಗಿ ನಾನು minus symbol ನ use ಮಾಡ್ತಾ ಇದ್ದೇನೆ. The output voltage is nothing but the current, output current Ic into the output impedance Z0 divided by the input current, that is nothing but Ib, into the input impedance, that is nothing but beta times of Re dash. But we know that beta is equal to Ic divided by Ib, and Ic can be written as beta times of Ib. That I am going to substitute here in this particular expression. Ic ಜಾಗದಲ್ಲಿ beta into Ib, Z0 divided by Ib into beta RE dash ಅಂತ ಇದೆ. ಸೊ ಬೀಟಾ ಬೀಟಾ IB ಕ್ಯಾನ್ಸಲ್ ಆಗುತ್ತೆ. ಸೊ ಉಳಿಯೋದು ದ ವೋಲ್ಟೇಜ್ ಗೇನ್ AV equals minus Z0 by RE dash. But the output impedance is just is equal to RC. So the AV is equal to minus RC divided by RE dash. But if the load resistance is connected, then AV will be equal to minus RC parallel with RL divided by RE dash ಅಂತ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತೀವಿ. ಸೊ AV is equal to minus RC divided by RE dash or minus RC parallel to RL divided by RE dash. Now let us calculate the current gain of this amplifier. So the current gain denoted by AI is nothing but the output current IC divided by the input current IB. But we know that beta is equal to IC divided by IB. So AI, that is the current gain, is just equal to beta. AI is simply equal to beta. So AI is nothing but beta only. And the last, that is the power gain. The power gain denoted by AP is nothing but the output power P0 divided by input power Pi, or simply the power gain is nothing but the gain of voltage, product of the gain of voltage and the gain of current. So this is the formula for the power gain of a transistor amplifier. So this is all about the AC analysis and the DC analysis of a common emitter configuration amplifier. So we have to do the DC analysis and AC analysis separately. While doing this DC analysis, what we are going to do is we are going to open the capacitors and the AC sources. While doing the DC analysis, we are going to short the DC as well as the capacitors. Now it's time to have a look on part 2 of this session. Hello everyone, welcome back to part 2 of the session. In this session, we are going to see about what is called as mechanical transducers. Mechanical transducers are a set of primary sensing elements that respond to changes in the physical quantity with a mechanical output. As an example, a bimetallic strip is a mechanical transducer which reacts to changes in temperature and responds with mechanical displacement. The bimetal, where bi stands for two metal, is made up of two separate metal strip, a piece of brass bolted to a piece of steel or iron. Steel or iron expands less than brass as it gets hotter. So the bimetal strip curves inwards as temperature rises. The bimetallic strip forms part of an electrical circuit. This is a picture where the bimetallic strip is placed inside an iron box. It is used to convert a temperature change into mechanical displacement. In this picture, we are having what is called as temperature adjustment cam. So it helps in adjusting the temperature of the iron box to silk or wool or cotton, etc. So with the adjustment of this cam, the temperature of the iron box can be easily varied. Accordingly, the bimetallic strip is going to work. So this is all about the part 2 of the session. Thank you. In this particular session, we discussed about the comparison of all the 3 configurations of amplifiers, that is common emitter, common base and the common collector amplifier circuit. Along with that, we also saw the DC and the AC analysis of an amplifier. In the next session, I'll be coming with a new topic. Until then, take care. Bye-bye.